Okay, this is going to be the first of a series of recordings on the topic of chaos, fractals, and dynamics. Primary resource is going to be Dr. Bob Devaney's book of the same title, Chaos, Fractals, and Dynamics, Computer Experiments in Mathematics. It's a small book written back, I guess, in the early 70s or so. Anyway, to get started on this, let's take a look at a function. I'm going to look at the function f of x equals x squared plus 2. And as you can see from the upper left-hand corner of the screen, this is on iteration. And so we're going to iterate, and let's see exactly what that means. To iterate on this function, we need a starting number, which we'll call a seed. And our seed is the first value of x we use, which is x0, and we're going to use a seed of 0. Use any number we want for a seed, but for the most part on these, as we develop this unit, we're going to use 0 for a seed, but not always. So let's go ahead and plug in. And so we're going to get f of 0 will equal 0 squared plus 2, which is 2. So our seed was x0, and our first iteration gives us x1 is 2. So what we do next is we take that and we plug that in for x. So we have f of 2 equals 2 squared plus 2, which is 6. So x2, our second iteration, is 6. And we're curious to see usually what happens when we iterate. And right now we can see we've gone from 0 to 2 to 6, so now we'll get f of 6, which is 6 squared plus 2, which is 38. And our numbers are continuing to get bigger and faster. Getting bigger faster. And then we'll get f of 38, which is 38 squared. Plus 2, which is lots. So x of 4 is lots. And then we plug lots in. F of lots will be lots squared plus 2, which is lots more, etc. Pretty clear in this case that when we do this iteration on f of x equals x squared plus 2, using a seed of 0, that we're going to get an ever-growing value for x, and in fact it's going off to infinity, or we'll say this diverges, or we'll sometimes speak of the orbit of x, which is this whole little list of numbers we have here on the right, and we would say the orbit of x escapes. Let's take a look at this iteration on your TI Smart View to see how we would do it on the calculator. Here's our little Smart View, and the way you do the calculator is pretty easy. You plug in 0 for x, so you put 0, enter. That's your starting number, your seed. Then we're going to put in answer squared plus 2. Now we don't put x, we put answer because we just got the answer of 0, and every time we hit enter we're going to get an answer. And then we'll plug back into this equation. So this, using answer instead of a variable, allows you to iterate. So let's do that now. Our previous answer was 0, so answer squared plus 2 is, hitting enter, 2. But hit enter again, remember it's the last equation, which is answer squared plus 2, so we'll take 2 squared plus 2 and give me 6. Then it'll give me 6 squared plus 2, which is 38. 38 squared plus 2, which is 1,446, what we called lots when we did it by hand. And then we square that and add 2, and you can see this is getting big. This is diverging very quickly. It's getting large quickly. And here we have 4.37 times 10 to the 12. And very quickly we exceed the capacity of our calculator, which I think goes up to about 10 to the 100th. So let's go back down there. Okay, so that's how we iterate, and different things can happen than what you've just seen, and that's what makes things interesting. Sometimes our function does not go off to infinity, and that could be related to the function, or to the seed. In this case, most of the time we're going to use a seed of 0, and we're going to change the function a little bit. Let's see how we're going to do that right now. Okay, so what we're going to do is, instead of x squared plus 2, we're going to go with x squared plus c, where c is any real number. It'll be a constant for that particular function, but since we're using it over and over again, we'll call it a parameter. So we have the parameter c that we're going to use to iterate on the function x squared plus c. And depending on the value of c, we're going to see what sort of iterations phenomena occur, if it escapes or whatever. So we've already done c equals 2. Let's try c equals 1. So then f of x will equal x squared plus 1. And we're starting with 0, so f of 0 is 0 squared plus 1. And then f of 1 would be 1 squared plus 1, which is 2. And f of 2 would be 2 squared plus 1, which is 5. And f of 5 would be 5 squared plus 1, which is 26, etc. And this wasn't any more interesting than x squared plus 2, because it still escaped. But let's go ahead and do it on our calculator anyway, just to get some practice doing this with the calculator. So again, we're going to have answer squared plus 2, but we're going to clear that out. No, I'm sorry, we're going to have answer squared plus 1. We put in 0, and then we'll go with answer squared plus 1. Notice you have to put in the seed first, and you go from there, and we go from there, and we get 1, 2, 5, 26, 6, 7, 77, and so on, and this is clearly growing without bounds. So we've tried two numbers. We've tried 1, we've tried 2. But remember, c can be any real number, and what we're interested in is the general behavior of this. So we want to try, essentially what we want to do is figure out a way to try all the real numbers. And to do that, we're really going to have to look for patterns, and we perhaps will want to get away from doing this by hand. So let's go to a piece of software on this. This is the free software program called GeoGebra, and it's been programmed to allow us to do what we just did, but maybe in a little more visual manner, maybe a little more quickly than you could do with your graphing calculator. So you'll notice I have here, I've set c equals 2. My function is x squared plus c. There it is. And over here I'm putting all my iterations, but you're also going to be able to see them graphed along this number line here, at least until they get too big. And up here is n, my number of iterations, and right now I have no iterations. So I'm going to start iterations. There are 2 iterations. You remember when we did c equals 2, we had 2 and 6 for our first 2 iterations. There they are. And right down here we're going to put our last several iterations, so we'll get like 100 of them, and all we really care about is the last few. We'll be able to see them here, and we won't have to go down the spreadsheet. Well, we know what happens in this case. The numbers just get really big, and there's 9 iterations for c equals 2. Now on our calculator, I believe that actually might have given us an error. I don't remember, but anyway, clearly we know that that's going to blow up. Let's go with c equals 1, which is what we did also with our calculator. And again, a seed of 0. And the c equals 1, you can see the numbers quickly, 1, 2, 5, 26, get very big. And they're graphed down here as well. We started with the c as 0, then we went to 1, then to 2, and then off the screen. Okay, well, I think if you just give a little thought to it, you'll realize that if c is bigger than 2, it's going to get even worse. It's going to get bigger faster. What happens when c gets smaller? That's what we want to investigate, because that's where it's going to get interesting. And so I'm going to go all the way down to 0.5. Just kind of splitting the difference between 1 and 0, and go ahead and do this. And we were hoping something different would happen, but as you can see, after only 10 iterations, it's growing without bounds. And if the number gets bigger than 2, once it gets bigger than 2, you know it's going to blow up. You don't have to go any further. Well, I'll tell you what, let's go on down to 0, see what happens. And so we go to 0. And that should not be a big surprise, because if you have 0 plus 0, you're going to get 0. So what we have here is that if C is 0, it's a fixed point. It doesn't move off of that. So at least I found something out here. Between 0 and 0.5, something happens. Something different is going on. Let's try 0.4. And 0.4, you can see, quickly blows up. Our GeoGebra tells us the number is so big it's going to call it infinity after 26 iterations. So let's go ahead and let C get smaller and watch what happens. Notice, C is getting smaller. I'm doing 26 iterations each time, which is plenty enough to show me that I'm still going way off the screen. Notice the dots are pulling in closer, but ultimately, once you get past 2, it's all over. Still getting very, very big, but not as fast. And now watch this. This point here, C is 0.26. We aren't all the way off to infinity. In fact, we're only at 0.781. It isn't growing that fast. So let's take our N. Oh, and unfortunately, it just took longer for it to go off and get big. So we were hopeful that something different might happen, but it didn't. But things are looking different now. So let's go down to 0.25. And again, we see it's not growing very fast with only, I have 15 iterations here. That's at up to 0.4464. So let's just go to 100 iterations. And this is looking more interesting. So I'm going to click on this slider bar. And instead of just doing 100 iterations, I'm going to let it go all the way up to 1,000 and see what happens. So here we go. And an interesting thing is happening. It looks like it's settling down. You have the list of all the numbers here. It looks like it may be reaching some sort of, maybe 0.499 is the answer. Let's go to our options. Click on rounding and do 15 decimal places, and we can see, well, it hasn't quite settled down, but it's growing more and more slowly. So we might speculate that maybe it's asymptotically approaching some number, and if I was a guessing man, I'd guess it's 0.5, and in fact it is, and later on we'll prove that in one of these little talks. Let's now take a break, because I'm trying to keep these things between 10 and 15 minutes. So you might want to go on your own and try 0.24, 0.23, 0.2, the numbers between 0 and 0.25 before you go on to lesson number 2. Okay, that's all for now.